Okay, students, we start with lecture number 19 now, and we will stick to the dioxide, albite, and anorthite phase diagram because there are several things that can be done, because this is also called the basalt system. I have talked about crystallization beginning with the melt composition that is in the plagioclase dioxide phase field, and then I have talked about plagioclase phase field, melt composition, the plagioclase turns field. And though the later part of the liquid line of descent is similar, but the early part we understand is different. When you're crystallizing pure phase, the line through the liquidous surfaces, until this means the boundary curve is quite straight. But if your initial crystallization is of a solid solution, then the path is curved until you reach the boundary line. Now in this, we try to do an important aspect is melting, equilibrium melting, because that is what is our ultimate aim in understanding cross-mantle interactions, the mantle melting and the formation of the crust. So that's what we do now for this phase diagram. So we have dioxide, albite, and anorthite, and this So that's the phase diagram, and you now know the isoplates. So the isoplates look like this. The isoplates look like this. And then we have the isotherms. Let me use a different color. So we have the isotherms which intersect like this. Now, having done this, you remember once again the importance of the isoplet. This isoplet merely indicates the locus of the composition of the plagioclase. Locus of the composition of the plagioclase in equilibrium with melts of different compositions at different temperatures. But the joining point here has no significance, because the actual plagioclase here would be to the higher anorthite contents. This I have talked before, and it's just re-emphasizing the point. Now let's say I take a rock. So let me take a rock which is R0, and it contains dioxide 40, and plagioclase 60, but you know this is not correct. So we write R0 is equal to dioxide 40. This is the plagioclase 60, but the plagioclase 60 can be albite 30, anorthite, albite 50, anorthite 50. This is the composition. These pens don't write well at all. Terrible. Okay. So this is my R0, the initial rock. So how do I plot the point? Diopside 40. So it's graduated. This is roughly diopside 50. So diopside 40 will be somewhere here. Here maybe. So we draw a line. So that's diopside 40. No. Diopside 40 would be here. So I draw a line like this, which is diopside 40. This is diopside, this is 50, 50. So let's say this is diopside 40. And then we have plagioclase and anorthite 50, 50. So you can see, you can have another line joining 50, and this will be your rock composition. This will be your R0 composition. Albite and anorthite 50, 50, and diopside about 40. So this to make up 60%, right? This is what we have. Now, the first question for Bill. What will be several things we always ask ourselves? Here we have not temperature of crystallization, we have temperature of melting, we have composition of the unmelted rock, we have the composition of the melt, we have the fraction of crystal is to melt, and so on. We ask ourselves several questions. So similar things we need to ask ourselves here. So what will be, say for example, if you have a rock R0 here, what will be the composition of the melt? That will the first melt composition that will form at the temperature. Which temperature? These red ones are the isotherms. So the isotherm passing through this point will tell you the temperature at which the rock will melt. And immediately the question is, what is the composition of the melt? Yes. So when you do that, you can see here there is a clue. Your plagioclase composition is albite 50 and anorthite 50. That means the plagioclase that is in the rock, and you have diopside, so the melt that will form. You will melt not only plagioclase, but plagioclase and diopside, because both exist in the rocks. So you will have plagioclase and diopside in equilibrium with the melt. So the melt composition has to lie on the boundary curve. The melt composition has to lie on this curve. Because not only plagioclase will melt, but plagioclase diopside will melt. And there will be a melt. And the melt composition should lie on this line. This boundary curve. The question is, where? The question is, where? The answer to this is, in this, the plagioclase that is there has the composition, plagioclase that is there has the composition anorthite 50. So you know what you have to look. You have to look for the anorthite 50 isopleth. The anorthite 50 isopleth. And since the melt composition is on the boundary curve, therefore, the point where that isopleth meets the boundary curve is the composition of the melt. So if this is plagioclase 50-50, then the corresponding composition, obviously, you can see the corresponding composition will be on this side. So this will be the composition of the melt. This is R0. This is R0, and this is the composition of the melt. So you will have a tie line. We'll have the composition. This is the tie line. Anorthite 50. This will be the line. You see, this will be, what is happening here, I don't know. Getting older, I believe. That's the tie triangle. You see here, this is your first melt that will be produced, L1. Do you understand? And R0 should lie on this line. But when you produce L1, melt L1, then obviously the rock in equilibrium, that means S1 will not be here. The S1 will not be here. The S1 then should be on this side of R0. So what you essentially do is take the point L1 and join it and extend it. Have you understood? You join it and extend it. So somewhere here you will have S1. Have you understood? You have to do the melting incrementally, very, very little. Incrementally. It's not possible to do it on the board. But say for example, you can say for example here, I draw the diagram again. This is the boundary curve. This is your R0. This is R0. This is your L1. So if you take this line and incrementally add it, this will be your S1. Is it right? This will be your S1. So essentially your phase diagram now will move to this. It will be joined on this phase diagram. And at the same time, if this is M and this is N, then you can see M divided by M plus N. M divided by M plus N is the fraction of the solid. And N divided by M plus N is the fraction of the melt, which should be very small for small degrees of melting. And your S1 should be as close as possible to this diagram. Have you understood? That will be your S1, or the residual solid with which L1 is in equilibrium. Residual solid in which residual solid S1, which is in equilibrium with the liquid. But as soon as you produce S1, have you understood? This S1 now, if you join, then you will have a plagioclase of a slightly different composition. And therefore what will happen with respect to this solid, you can read it from here, and when you read it from here, you can find out the corresponding melt fraction, the corresponding isopleth which meets the boundary curve. And so you will have another tie triangle. Now this time the tie triangle looks like this, and this is your new S2, and then it shifts to S2. So this is how the triangle will move, will swing in the opposite direction. The triangle will swing in the opposite direction as your S0 here, which is anode type 50, as you melt it, the anode type becomes, the plagioclase becomes more and more anode type rich. As it drags as the changes of the plagioclase, as it moves towards more anode type content along this direction, have you understood? It will encounter isopleths which has more anode type rich. This will cause the liquid composition along the boundary curve to move in this direction. Have you understood? Now, another point is, as the liquid moves in this direction, say let's say L4 at this position, so your reaction boundary as your tie triangle should move further, and you will have PL4, S4 dioxide, and L4. This is the new triangle that is formed. And you can see your N1 extends. That means the fraction of the melt is extending, although m remains constant. As you do this, go on doing it, this point will reach this point. Or for example, have you understood? This is where you will finally reach, where you pass your initial R0, where R0, this rock composition 0 will be bracketed between, now not a tri-triangle, but a tie-line, not a tri-triangle. Previously, this R0 was within the tri-triangle. But when the melt composition moves along the boundary curve and occupies such a position where the R0 is straddled between this melt composition and this line, that means it lies on a binary. It lies on a binary. Then you can see at this, when it lies on a binary, that means what is happening at L4? At L4, when it is joining this binary, then if you now melt the solid composition, so now the melt will move now in this direction. These pens are just bad. Have you understood? So what happens in this? Now this one is wrong. So now you see when you're tri-triangle, then you are on this line. Have you understood? You are on this line. That means dioxide is no more is exhausted in the rock. Why? Because now your rock composition lies between this melt and this plagioclase. So what has happened is, at this point, dioxide is completely exhausted. The last crystal is just being exhausted. Why? Because in the previously, the R0 composition was within the tri-triangle. Now, the R0 composition here, R0 composition, lies on the binary of what? The solid composition, the melt composition, and the solid composition. So now there is only two phases that are in equilibrium: plagioclase and melt. Dioxide is just about exhausted in the system. It's completely exhausted in the system. And another thing I should tell you, when we were from L1 to L2 to L3, I also told you, remember, you can join these lines. R0 is here, so this line you could join, this line you could join, and this line now is here. So previously, these points would have given you the solid composition proportion of plagioclase and dioxide. But when you have a tie line here, then there is no plagioclase, no dioxide. There will be no dioxide now, because obviously the initial rock composition lies between the melt and this plagioclase 4. Have you understood? So what is happening here? From here to here, if someone asks you the question that how will we find that dioxide is exhausted? The answer is simple. When the rock composition will lie on the plagioclase dioxide binary and not within the plagioclase dioxide melt phase triangle. It will lie on melt plagioclase binary. But so long dioxide persists, the rock composition R0 should be lying within the triangle. once the triangle has rotated so that the rock composition lies between plagioclase and milk, there is no more dioxide. So now your rock contains only a plagioclase. Have you understood? Now what happens? I will again just quickly take you back, because equilibrium crystallization is the reverse of equilibrium. Equilibrium melting is just the reverse of equilibrium crystallization. So I will draw the boundary curve, I will draw the base, and I will draw the diagram for crystallization. So what happened? Let's say there was L0 here. This was the initial composition. So what happened to the path? The path was like this, where you had do you see that? That was how the path looked like. This was the path that was followed by the liquid. This was the path that was followed by the liquid during crystallization. Right? Now we are talking of melting. So you can imagine that the whole process would be a reverse. What do you mean by when I say the whole process would be reverse? During crystallization, what was happening? The plagioclase compositions were becoming more albite rich, right? The ratio of this by this was changing, this versus this was changing, so that the melt fraction was decreasing. Melt fraction was decreasing means these segments of the lines became shorter and these segments of the lines became longer with crystallization. Now, during melting, this will be just the opposite. So once you have a melt composition here, so if your rock composition is somewhere here, if your rock composition is somewhere here, and your melt composition, this was the tie line which I showed in the last diagram. This was the tie line. Yes or no? Now what will happen? Now you can understand that the unmelted plagioclase will become more anorthite rich, and the path followed would be just the reverse. You have to do both simultaneously. Have you understood? And all the while, these tie lines should pass through R0 for equilibrium melting. So what will happen? If you are here, this is the rock composition, so you are on this binary. This is plagioclase here, plagioclase 1, and let's say this is L1. Now what will happen? If you take another composition, plagioclase 2, what will happen if you take the plagioclase composition, say plagioclase 2, and you take, say for example, there was 50% crystallization. Now you the melt fraction. Now the melt fraction was say 0.5. Sorry, the melt fraction was 0.5. Now, if you increase, because you're melting, you increase the melt fraction to 0.55. Have you understood? Melt fraction as 0.55. So, if you have plagioclase 2, then you have to draw a line where this ratio and the corresponding ratio here should give you a value of 0.55. Have you understood? That means if these ratios are n and these ratios are m, then m divided by m plus n is the fraction of melt. Is the fraction of melt. So once you keep plagioclase to, you know this distance. If you know plagioclase, then you know distance. What is this? You know n. What you want to find out is n. So m divided by m plus n, which is the fraction of the melt, is 0.55. So your m is equal to 0.55 m plus 0.55 n. So you have 0.45 m is equal to 0.55 n. So n will be equal to 0.45 divided by 0.55 m. So if you know m, if you know this is the plagioclase composition, you take this, whatever the length is, it does not matter. The size of the ternary diagram does not matter. If this is 0.55, you write down the length of m and multiply it into this, and therefore you will get the length of n, which should be on the same line as this but extended here. Then you get another point. I will repeat again. Say I want to find out here, so whatever, say L1 and PL1, this was an equilibrium. Now I want to find out where will be L2 and PL2. I want to find out where will be L2 and PL2. So I take arbitrarily a composition close to PL1, which is PL2. Let's say this is the point PL2. I know the composition of the plagioclase, PL2. But I want to know the point at which L2 is. The point at which L2 is. It's not on the boundary curve. You see, in this isoplate, if you are away from the boundary curve, here it can exist all along the line. All along the line it will exist. So what happens if you take plagioclase 2, and this is m, this segments are n, and this segments are n, and if you know the melt fraction from here, of course you know, because you know this m and n, you know. So now you want to increase the melt fraction of 0.55. Then you take m divided by m plus n is the fraction of the melt. So you do this m into 0.55, from which you get this value. So if you know m, you can find out the n. So at the end of n is what is L2. So similarly, if you go from L1 to L2 to L3 to L4, and finally when n is equal to 0, n is equal to 0 means the fraction of melt is n. N divided by m plus n is the fraction of melt. N divided by m plus n is equal to fraction of melt. Right. If you have a melt fraction 0.55, then you do this and then you do this. So when should all the rock be exhausted? Or melt should be 100%. That's the point. When will this process end? When will this process end? When n, which is the fraction, n divided by m plus n is the fraction of the solid. N divided by m plus n is the fraction of the solid. So when n becomes equal to 0, then your m becomes equal to 1. M becomes equal to 1 means fraction of melt is equal to 1. That means the whole solid has undergone melting. So this is how melting can also be predicted. Equilibrium melting can be predicted using this phase diagram. Let us now try a situation where If you have any question, please let me through. It would be very difficult, but if you have questions, it is better that I will write it. If it is more complex, I will write it in the video lectures, or if there is a straightforward answer, I can write to you for the whole class. But if it's a more complicated question where drawings have to be done, then I have to take a separate lecture, answers to your questions, so I can give you that way also. Now another point is, say for example, you have a rock whose composition is, this is the boundary curve, and your composition, this is R0. This is R0. So what will you do now? This is R0. So how to start? This is dioxide, this is albite, and this is anorthite, and this is a plagioclase phase field, dioxide phase field. So if you have a rock, R0, how will melting proceed? So you can see, you take a rock and you join it. You take a rock and you join it. So what happens? And you draw a line like this. So you know the composition of the rock in terms of diopside, albite and anorthite, or plagioclase proportion. Within plagioclase, the proportion of albite and anorthite, it's well known now. So if this is the composition of the plagioclase, then you find out composition of the isopleth. Remember, your rock has both diopside and plagioclase of this composition, right? Now, if you have to melt the diopside and the plagioclase of this composition, so the melt has to be on the boundary curve. That's for sure. The melt has to be on the boundary curve. That's for sure. So now, what will you do? You take the plagioclase composition here and look for the isopleths and see how the isopleth moves and where it joins the boundary curve. Now, here, if you join, this is your first triangle. This is your first triangle. The first drop of melt that will be produced is here. The first drop of melt that will be produced is here. This will be the proportion, as you can see, if you can take a line and join it, this will be the initial rock, which will be on, because if you produce a very small amount of melt, the rock composition does not change so much. So what happens? This is the proportion of diopside, and this is the proportion of plagioclase, and this gives you the albite is to anorthite ratio of the plagioclase. So your first melt composition would be L1. But as soon as you produce L1, not the first drop, but after 10, 2%, 3%, 4%, 5% melting, this line has to extend. This line has to extend. Have you understood? After some amount of L1, this line has to extend. And depending upon 2% or 3%, you can find out this will be S1. So now, you take dioxide and you join S1. So this is your S1 composition. Look for the isopleth. That isopleth would be anorthite rich. Richer. That isopleth would be richer in anorthite. So, if it's richer in anorthite, then your L2 composition will shift into this direction. And then, so this will be your, this is plagioclase composition. And so your L2, if you pass through R0, it will make a point and you will have a tight triangle for that. So this way you can go on till you reach. So you can go on melting the plagioclase making it an orthite rich, and also you can find out what is the segment of the composition, because your melt composition, this one takes it. So your plagioclase, so your triangle goes on rotating the anti-clockwise way, and when you do that, at one point of time, this melt composition will coincide with R0. This melt composition will coincide with R0. It will lie on the base of it, for which there will be a plagioclase and this composition. This will be the last composition where plagioclase of this composition, dioxide pure, and melt will be in equilibrium. And melt will be in equilibrium. But you can see that at the last phase, if it leaves the boundary, then you see your melt composition in the next step. The melt composition moves from here to here, and plagioclase is no more there in the rock. Plagioclase is no more there in the rock. So this is how melting can proceed. So wherever the rock composition or the melt composition is, you can predict what will be the temperature of melting, what will be the composition of melting, what will be the composition of the solid, what will be the composition of the melt, what will be the proportion of the mineral in the solid. All this can be determined. I will give you an advice. I will give you several advices at this point of time. In the internet, you will find ternary diagrams. Ternary diagrams are there. Ternary diagrams. Also in the internet, you can find out that if you type dioxide, albite, anorthite ternary system, you will find the positions of the isotherms. You will get a diagram which will show you the temperatures or the isotherm distribution. In fact, the numbers, temperature of melting, each isotherm will be given a melting temperature. Normally in the class when we are there is no physical class now, so I can't tell you here from here. But I used to sit down one Saturday evening, and all the students used to do this calculation and draw variation diagrams, etc. So they could find out all parameters, how they change during melting. It was a 6-hour class, starts from 8 o'clock in the morning and finishes at 5 o'clock in the morning. But here I can't do it. And when you do those types of calculations, it becomes much more easier for you to see how things are working. So what you will have is, when you do this dioxide, albite, anorthite ternary, you will get a diagram which shows you the isotherm. Also, you will get a diagram which shows you the isoplates. So you superimpose the isoplate and the isotherm diagrams on a ternary. Right? Now, say best is to start with crystallization. First, you take any point, anywhere, as L0. Take a scale and a pencil and a calculator with you. Write down the values and you pinpoint the points where you get the melts. But remember, don't do it arbitrarily. Always ask yourself, why am I doing it? Why am I extending it? Why should I do this? What is the melt composition? What is the temperature? What is the proportion of the crystal? You go on asking yourself this question for every step that you do. If you can do that, you will be understanding ternary phase diagram, solid solution phases, how solid solution phase diagrams can be used to find out different parameters you can find out. You can do this. Basically, take an isoplate diagram of dioxide, albite, and anorthite. Take an isotherm diagram. If you in a particular book, sometimes both are superimposed. So then it's fine. You take a nice photograph and you put it on a sheet and take a printout. Take a pencil, take an eraser, and take a scale. And now you do these calculations yourself. And you will say, for example, you take an arbitrary point L0, anywhere, somewhere, L0, and you track the liquid line of descent. I will suggest you, if you are interested, start from the dioxide one first. It's much better, it's easier. If you start with plagioclase, it's also easy, but a little tough. You might get lost in the middle. So what I suggest to you, start with the dioxide and see how you arrive at the last liquid composition logically. And every point that you do, you ask yourself, what is the temperature? Write it down. What is the composition of the melt? Write it down. Say diopside 60 or albite and orthite 60 or whatever. Write down the composition. What is the composition of the solid? You can find out geometrically what is the composition of the solid. Proportion of the mineral, how it is. Crystal melt proportion, what it is. So do it. I think all of you should do it. If you do it once with your hand, you will understand it much, much better. Using all the clues that I have sort of given you. Once you have done from the diopside, early forming crystal diopside, then repeat it for the plagioclase composition. Say, for example, a melt composition where plagioclase is the early form of crystal. You try to do it. And you will find that you are understanding it much better. Once you have done it, then you do it for equilibrium melting. And whatever clues I have given, you can use that and do it. I will suggest to you, you do it once, twice or thrice. You understand it better. Otherwise, you think you understand, but essentially I can better it that you really did not understand. I can better it. It is not, it is easy, it's logical, but unless you do it the hard way, you really don't get the hang of it. So that I think you should try and avoid always. Always try and avoid that. Do it yourself. I request you, because this is not a normal physical class, so I would have made you sit in a whole Saturday, 8 o'clock to 5 o'clock, and after that you know phase diagram much better. Because you know where you made the mistakes. You know what is right and what is wrong. So I used to make pairs, so two people together, do a calculation. Many people used to do in laptop. They were faster. Many people used to do it in laptop. Those who are very conversant with Excel spreadsheets, they can do it very fast. And they in fact show you the liquid line of descent. So in fact, one year, I don't know which year it is, but about 6-7 years ago, there was a person in your class, MTech class, not your class, MTech class, who was very good with programming. And he told me that, sir, can I do a programming of this? So you give the R composition, I give you the liquid line of descent. I said, do it, and I distributed it amongst all the faculty members of this department. He was so good. So you just give a point and it tracks the liquid line, and it shows you 0.5, 0.05, 1, 0.1, the compositions. If you want, and there's a box where you say initial composition, liquid, raw. You say whichever one, give the composition, and then you tell what intervals of fractional equilibrium melting or equilibrium crystallization, and he did it. And it was just like a video. It showed with all the values on the table. We were stunned. The whole department was stunned. But he was very, very good with computers. So you can do that absolutely correctly. But I think you need to sit down. I'm sorry that I could not do this to you, but you can do it myself. And if you have questions, you can ask me. I will try to help as best as I can, but there is nothing like a physical class. There's nothing like it. This video lectures, I don't like it. I have to do it because I'm paid. But if you had left me alone, I wouldn't have done it. I don't like to take classes this way. This is not my way to take class. Classes where you really sit down, interact with the student, and tell them, okay, this is right, this is wrong, okay, this is why it's not right, this is why it's wrong, and then you learn much more. This type of teaching is not helping. I don't think it's helping. But anyway, I leave it to you. Thank you very much.